All right, good morning. Again, just resuming with what we have been working with polynomial and rational functions, and just sort of going back to looking at forming polynomials from given zeros. And we have on page 281, okay, and now here we're looking at forming a third order polynomial. In problem 72, okay, we have the following. Okay. We have the zeros, and each of these will be a multiplicity value 1. And among the zeros, we have 1, -6, and 3. And once again, the order of the polynomial is going to be 3. And just looking at least setting up the factored form, or one factored form of this polynomial. Okay, so we have with x is equal to 1, we can say that this stems from x minus 1. And then for x is equal to -6, we'll say that the corresponding factor is x plus 6. And for 3, okay, we're going to have x minus 3. And looking at what we have in the formation, okay, so as we are looking at expanding, okay, if we multiply x minus 1 and x plus 6 together, okay, and we're going to have for the product of x minus 1 times x minus 6. So again, we're going to have x squared, and we have plus 6x minus x, which will leave us with 5x. And we have minus 6. And this will be multiplied by the quantity of x minus 3. And looking at what we have upon multiplying. Okay, so if I just set up a row column display, and again, this could be a 2x3 or a 3x2. And I'll just have this as a 2x3, like 2 rows, 3 columns. And just looking at what we have in correspondence. Okay, so for taking what we have with respect to the immediate products, okay, so we have looking at it going column by column. Okay, so we have in the case of the first product case, so we're going to have x squared times x. Okay, so that is going to be x cubed. And then for what we have upon completing what we have in this first column, so we have -3 times x squared. Okay, so we have in the bottom section, okay, we'll have -3x squared. Then for the next column, we have x times 5x, so this will be positive 5x squared. And then we have, in the middle, we have 5x times -3, so this will be -15x. And then completing out the last column, okay, we have -6x. And last part, we have -6 times -3. Okay, so this will be a positive 18. And so in looking at what we have for the results here, so we have for f of x, again, we have x to the third. That is the only cubic term that we have in the set. And then we have in x to the second, so we have a -3x squared plus 5x squared. So this leaves us with a positive 2x squared. And we have for the first order in x, we have coefficients -15 and -6, and those will combine to -21. And then we have for the constant in this particular case, right, so we have plus 18 at the end. And so an expanded polynomial that is third degree in x, and that will have those particular zeros. Again, if you're to set this particular polynomial equal to 0, and then you factor, you would get this set, and setting each one to 0, you would have your solutions in x to be 1, -6, and +3. Now, where we have the inclusion of non-integer valued zeros, for number 74, okay, so we have zeros listed at 2 and 5/2. Now each of these will have a multiplicity of 1. Okay, now we have for the third zero, okay, so this one is going to have a multiplicity of 3. Again, the multiplicity of 3 applies only to 0. And for the degree, now we have for the factors corresponding to the zeros of 2 and 5/2, each of these will be a first degree. And then for 0, the corresponding degree will be, in the factor, will be third order. So you got 1 + 1 + 3, so the degree is equal to 5. And looking at what we have in setting up a factored form. So we have with 2, okay, so I have x minus 2. And we have for 5/2, now we can initiate by saying we have x minus 5/2. And for 0, okay, now we're starting out with x, and since 0 has a multiplicity of 3, okay, we're going to have x to the third. And once again, I'm going to copy this because there are various ways that you can go about this, okay, and you can have an expanded polynomial with or without integer coefficients. And let's say that if you were to take care of the fraction, taking this approach. Okay, so you have f of x. And we can rewrite, so we have x minus 2. And then we can raise the coefficients for x minus 5/2 by taking care of the halves, multiplying by 2. Again, we have multiplying by x cubed. So you have f of x. Okay, so you have x minus 2. And just raising what we have in the middle factor, okay, by 2. Okay, so you have 2x minus 5. And we have times the cube of x. And just looking at multiplying together what we have in the first two factors. Okay, so and we have f of x is equal to, and for x minus 2 times the quantity of 2x minus 5, so we have 2x squared. And we have minus 5x, and you have minus 2 times 2x, so we're going to have a minus 4x. So this will come out to negative 9x. And then we have negative 2 times negative 5, okay, it's going to be a positive 10. And once again, we have multiplied by x cubed. And so we have as one possibility, okay, so taking this product and multiplying by x to the third. So we're going to have 2x to the fifth minus 9x to the fourth plus 10x cubed. Okay, and if you were to have kept the fraction, again, this is just another possible approach. So you have x squared. Now you're going to have a negative 5/2 x and a negative 2x. And think of this like negative 5/2 x minus 4/2 x. So this would be negative 9/2 of x. And negative 2 times negative 5/2. Okay, that's going to be a positive. 10 over 2 is going to be 5. and multiplying by x cubed. And then we have distributing. Okay, so you have x to the 5th minus 9/2 of x to the 4th plus 5x cubed. Okay, so this is going to be yet another possible result. Okay, for you're still going to have a 5th order polynomials, and if you were to set this expression as well equal to 0, you would still come out to the very same 3 solutions for x. All right, now just kind of going back to what we looked into on Friday, okay, with asymptotes and domain, vertical asymptotes and domain. Now we have, in the case of, for that particular set, and we have in the case of, say, for the first item, okay, so we have polynomial function f of x, okay, and we have is equal to x squared minus 25. And we have all over x minus 5. Okay, and again, in looking at what we have with this polynomial function case, so if we look for the domain, okay, what's going to happen here, okay, is again for the domain, you look at this before you simplify. Okay, so we have the x minus 5 cannot be 0. So we have that x cannot be equal to 5. Okay. So we have in the case of the domain, okay, so you have all real values except for 5. Okay, so for the domain, you have first half will be those values of x less than 5. And then for the second half, we have those values of x that will be greater than 5. And so that will be the interval notation. Now, again, this function is not in simplest form. And for vertical asymptotes, those are going to be resulting from exclusions from the domain whose factors will remain in the denominator after the rational function is simplified to lowest terms. And here we have with x squared minus 25. Okay, we have factoring out to the quantity of x plus 5 times that of x minus 5. And we have over x minus 5. Okay, and here x minus 5 is going to cancel out. And the reduced result, okay, is going to be f of x is equal to x plus 5. Okay, so here, x minus 5 cancels out. And so if the factor cancels, then that exclusion from the domain is going to be a hole in the function. And since x minus 5 cancels, if you notice in the end result, okay, there's no denominator, so there'll be no vertical asymptote. So there's no denominator in the variable x. Okay, so there is no vertical asymptote. Okay, and just providing a little bit of a visual on this one. Again, just the x value of interest, okay, that was at 5. And in terms of the graph itself, okay, now for the appearance, okay, what's going to happen here? Okay, just to mention, now this would be the graph of y is equal to x plus 5, but the difference, instead of starting out from y is equal to 5, we started out with this rational function instead of having it run continuously, as opposed to if it had been y is equal to x plus 5. Again, is from the start that we have 5 was excluded, and again we have a hole in the graph at x is equal to 5. Okay, and now for what we have in the case of the next item, okay, now we're going from f of x to g of x. And for this function case, you have x squared minus 9 all over x minus 3. Okay, so if we're looking for the domain and any vertical asymptote, okay, so again we have an x squared minus 9 over x minus 3. Again, the denominator cannot be 0. And so we have that x cannot be equal to 3. Again, just like what we had earlier, we have one exclusion from the domain, and this time the restricted value is going to be at 3. Okay, so we have that domain laid out, okay, in the interval notation. And for what we have in the case of looking for the simplified form of g of x to see what comes out of this. Okay, so we have, once again, we have x squared minus 9 all over x minus 3. So we have a little bit of history to repeat. For the numerator, again, is going to be a difference of squares. And we have, in the difference of squares, we have a factor that is identical, okay, to what is in the denominator. Okay, so we have the follow-through to be, once again, the same. Okay, so you have x minus 3 cancels out. And instead of having what could have been a vertical asymptote with x is equal to 3, it turns out that x equals 3, just like x equals 5 earlier, is going to be a hole. And we have just with this reduction, okay, so g of x, okay, is equal to x plus 3. Okay, and so we have no denominator in x, or in the variable x. Okay, so we have no vertical asymptote. Again, just like 5 earlier, okay, so we have a hole located at x is equal to 3. Okay, so this will be the dynamic case. So we do have a whole, once again, x is equal to 3. All right, now looking at what we have, again, with vertical asymptotes, and we have for number 17. Okay, so we have a function f of x is equal to 8 over x minus 4. And I'll just go ahead and mention, okay, so with f of x equal to 8 over x minus 4, okay, we're going to have already that f of x is already in simplest form. So the exclusion from the domain is going to be a restricted value that is going to define the vertical asymptote. So we have with the denominator, okay, looking for the domain, so you have x minus 4 cannot be equal to 0. So to keep the ratio defined, okay, x cannot be equal to 4. So you have with the domain, okay, so you have it to consist of those values of x less than 4, and also those values of x that will be greater than 4. And since f of x is already in simplest form, that means that x minus 4 remains or does not cancel. So this signifies that the exclusion of 4 is going to become the vertical asymptote. Now I'll just use VA, shorthand for vertical asymptote, and this is going to be at x is equal to 4. Again, we have the excluded value of 4. And in the case of what we have with the activity, okay, for f of x equal to 8 over x minus 4, and once again we have with the vertical asymptote x equal to 4. Okay, notice that as y decreases, you have this portion is getting closer to the vertical asymptote, and then as y increases, at least on the left hand side, you have this portion is going to run tangent. But again, vertical asymptotes are going to be off limits. And this will be the general behavior of what we have with this function f of x, again, which will be split into 2 distinct sections thanks to the vertical asymptote x is equal to 4. Now, in the case of what we have with number 18, at this time we have with this rational function, here we have g of x is equal to 2 over x plus 7. And just like f of x moments ago, okay, we have 2 over x plus 7. It's already in simplest form. And instead of canceling, okay, so you have x plus 7 is going to remain. And regarding the exclusion from the domain, okay, so you have x plus 7 cannot be 0. Okay, so we have the x cannot be negative 7. So you have one exclusion from the domain. Okay, so you have a little bit of history to repeat where you have those values of x less than the exclusion at the minimum, and then you have at the maximum, you have those values greater than the exclusion. Okay, so we have at the lower end, we have parentheses surrounding negative infinity and negative 7. And at the upper end, we have parentheses around negative 7 and positive infinity. And again, since x plus 7 remains, again, this restricted value defines the only vertical asymptote there will be. Whereupon the vertical asymptote we now have to be at x is equal to negative 7. Okay, so you have negative 7, vertical asymptote. Again, we have with the graph. Okay, so much of it is going to run tangent to both the x-axis and the vertical asymptote, x equal to negative 7. And again, just like f of x, g of x, we have again to be split up into two distinct sections. All right, now for what we have in the case of the next item, okay, and we have for number 20, okay, now you're looking at a function k of x is equal to x plus 2 all over 3x squared plus 8x minus 3. Okay. Now, in this one, okay, so we're going to expand the model a bit. And let me give you just a little bit of a backdrop. Okay, now we have with the denominator, okay, so we have a 3x squared plus 8x minus 3. And instead of going ahead and tackling the domain right away, if you notice, we have with the denominator, okay, so you have 3x squared plus 8x minus 3. And if we look at factoring, okay, again, so if you factor by grouping, okay, so you have 3 and negative 3. And that is equal to negative 9, okay. And again, so we have finding factors of negative 9 whose sum or difference will be on the plus side at 8. Okay, now we started out with 3 and negative 3. Now first and last coefficients. And if I multiply together, have 3 times negative 3 is negative 9, and adding 3 plus negative 3 comes out to 0. But I want a positive 8 sum. And I tell you what, just in the rewrite, okay, if I place the negative factor in front, say I have negative 1 and 9. Negative 1 times 9 is negative 9. Negative 1 plus 9 comes out to positive 8. So this will be the combination that we seek here. And so just taking what we have and splitting up. All right, so we have 3x squared. Again, it doesn't matter which one comes at the front, but I will say in terms of grouping and not worrying so much about the factoring out of negatives and making sure your sign terms are correct, I normally place the negative factor or term in front of the positive, just to ensure that the middle operation, once we group together, will be addition. Okay, so looking at grouping together. Okay, so I have 3x squared minus x at the front. Again, we have operation of addition in the middle. Okay, and I have plus the quantity of 9x minus 3. And looking at factoring. Okay, so, all right, so I have 3x squared minus x. Okay, now the greatest common factor here, okay, that is going to be at x. X into 3x squared is 3x. X into negative x is going to be minus 1. And bringing down the addition. Okay, so the greatest common factor of 9x minus 3. Okay, that is going to be at 3. And 3 into 9x minus 3. Okay, that is also going to be 3x minus 1. So you have in factoring, okay, so you have 3x minus 1, which is shared. Then we have times the quantity of the outside terms in operation, which in this case is going to be x plus 3. Now, with our function k of x, okay, so you have k of x. Okay, so you have x plus 2 all over 3x squared plus 8x minus 3. And just taking what we have here and looking for the domain exclusions. Okay, so if I have, again, so if I have 3x squared plus 8x minus 3, cannot be 0. Okay, so once again, looking at factoring, okay, so I have the quantity of 3x minus 1 times that of x plus 3 cannot be 0. And looking at itemizing. The factors, okay, so 3x minus 1 cannot be 0. So this means that 3x cannot be 1. So we have a non-integer value excluded from the domain. Okay, so we're going to have that x cannot be 1/3. And as for x plus 3, x cannot be negative 3. And so we're going to have, in the case of the domain, we have two values excluded with negative 3 and positive 1/3. Okay, with negative 3 as the smaller of the exclusions. Okay, we have at the lower end. Okay, we have those values. Okay, that will be less than negative 3. So we're going to have parentheses around negative infinity and negative 3. Then we have next up, we have those values, okay, that will go past negative 3 and approach but not include 1/3. and 1/3 as the second and last exclusion. We're going to have the rest of the domain will be those values of x that will be greater than 1/3. Okay. So this is going to be the domain. Okay. And looking at what we have regarding the vertical asymptotes. Okay. Okay, so we have x plus 2. Again, we have for the factored form in the denominator. Okay, so you have 3x minus 1 times the quantity of x plus 3. So this is going to signal that k of x is already in simplest form. So that means that both of the denominator factors remain. So they're not going to cancel out. So this is going to mean that we have not one but two vertical asymptotes. Okay, and so we have with these, okay, so you have x equal to 1/3, as well as x is equal to -3. Okay, so not one but two vertical asymptotes. Okay, so just looking at what we have in the structure. Okay, so you have x equal to -3. And x equal to 1/3, so we have again two vertical asymptotes. And in terms of how k of x is going to be played out, you'll have to split up not into two but three distinct regions or sections. And again, both of the vertical asymptotes are going to remain untouched. And these three sections will be in reference to what we have defined for k of x. All right. Now, and let's say that just for the next few moments, and then we'll get into other categories, okay, regarding asymptotes. Okay, say if you're looking for the domain and vertical asymptotes. We'll say we have r of x is equal to x squared minus 25 all over x squared plus 7x plus 10. Okay, if we start out looking for the domain and seeing if there are any exclusions, again, you're looking for the domain before you do any kind of simplifying. And we have in the denominator, okay, which cannot be 0, we've got x squared plus 7x plus 10 and if x squared plus 7x plus 10 cannot be 0, then neither can its factors. Okay, so you have the factors at x plus 5 as well as x plus 2 and if these factors cannot be 0, okay, so we have two exclusions from the domain, okay, and those will stem from excluding x plus 5 as well as x plus 2 from equaling 0. So if x plus 5 cannot be 0, okay, we have the x cannot be negative 5. And if x plus 2 cannot be 0, we have the x cannot be negative 2. So you have in the case of the domain, and lining things up, okay, so you have starting from negative infinity, approaching the smaller of the zeros, in this case negative 5, but not including negative 5. And then we have for the second portion, okay, we have those values greater than negative 5 and less than negative 2. Again, negative 2 is going to be bypassed. And the rest of the set defining the domain will be those values of x greater than negative 2. Now, crossing over into the realm of determining asymptotes. Okay, so you have with the ratio r of x equal to x squared minus 25 all over x squared plus 7x plus 10. Okay, now we have this ratio is not in simplest form. And if we look at factoring, so we have with x squared minus 25, we have this difference of squares to reappear. And again, we have the quantity of x plus 5 times that of x minus 5. And for x squared plus 7x plus 10, we have the quantity of x plus 5 times that of x plus 2. If you notice, okay, we have a common factor with x plus 5. So you have x plus 5 is going to cancel out. And there's no x plus 5 left over in the denominator, so x equals negative 5 is a whole. And we have for the simplified result, okay, we have x minus 5 all over x plus 2. Okay, so we have, in this case, x plus 2 remains. So there could have potentially been two vertical asymptotes, but with x plus 5 canceling out, we have instead one whole and one vertical asymptote, and the lone vertical asymptote we're going to have at x is equal to negative 2. and just looking at what we have, at least for the dynamic. Okay, so we've been looking at, once again, just domain and vertical asymptotes, and there will be other types. Okay, and let me just mention, in case you have x equal to -2. Again, that is the only vertical asymptote we have. And in the case of the graph of the function itself, okay, so again, the other value we had in play was at -5. Okay, so this is what we have so far with r of x. Again, we have a hole at x is equal to -5, and it's going to be located in this particular upper section. All right. Now, again, so we have one vertical asymptote at x equal to -2, and stemming, okay, from the remnant of x plus 2 in the denominator after r of x is completely simplified. And again, with x plus 5 canceled out, okay, we have x equals -5 is going to be the location of the hole itself. Okay. Now, again, with other types of asymptotes, and we're going to have for the next categories, and this is going back to what we have for rational functions expressed as ratios of polynomials. And the other types of asymptotes we're going to have in play will be horizontal and slant asymptotes. Okay. And it's kind of going back, and we'll use a couple of theoretical notations. For a rational function, okay, we have r of x. Now the numerator is going to consist of terms, okay, that you have already seen, like with the in behavior and the polynomial division portions. So we have in the numerator. Okay, so you have, once again, have a of n, x of the n, plus a of n minus 1, x of the n minus 1. And you can have going all the way down to a naught, where a naught is just going to be a constant once you put in terms of application. Now for the denominator, we have the letter b as a coefficient and subscripted by m. So you have b of m times x of the m. And we have plus b of m minus 1. And you have x raised to the m minus 1. And we have, just like the numerator, okay, the denominator polynomial, okay, is going to end with the constant, and that's going to be symbolized by b naught. Okay, so for this rational function, we're going to have n is going to be the degree of the numerator, and the letter m. Okay, that's going to be the degree of the denominator. And we have in the setup. Okay, now there are going to be some comparisons. Okay, first of all, if we have that the degree of the numerator is less than what is in the denominator. Okay, so we have if n is less than m, then there is a horizontal asymptote. And that horizontal asymptote is going to be y is equal to 0. Now, if we have the n relates to m, where we have the n is equal to m, okay, now you're going to have another horizontal asymptote, but this one is going to be non-negligible. And we had the y is equal to a of n, that is the highest order term coefficient in the numerator, divided by the highest order term coefficient in the denominator. So you have a of n over b of m, and that is going to reduce to a non-negligible constant. Okay, so comparing n to m, so you have going from less than m to equal to m. Now, if we cross over to greater than, and we have by 1 degree, in other words, if n is greater than m by 1, okay, then there is going to be what is referred to as a slant asymptote. And the slant asymptote is going to be a straight line. And the way I'm going to express this is going to be like another way of writing the slope-intercept form. Now, normally I would say y is equal to mx plus b, but I've already used up m as the degree of the denominator. So I'm going to say I have y is equal to alpha x plus beta. So alpha would be like the slope of the slant asymptote. Beta would be the y-intercept. Okay, so if n is greater than m by 1, then you're going to have a slant asymptote. And if we have that n is greater than m by more than 1, way to summarize this is that you're not going to have any horizontal or slant asymptote. So I'm just going to kind of stress here. So you have no horizontal asymptote, like no HA. Also no slant asymptote, so you have no SA. Okay, so if there were to be any asymptote, it will be just the vertical asymptote. And let's say that, for instance, if we're looking for domain and asymptotes, And we'll see we have in the first case. All right, so we have r of x is equal to 3x plus 1 all over x plus 2. Again, so I'm going to start out with one that is already in simplest form. And regarding the domain case, you have the denominator, we have x plus 2. X plus 2 cannot be 0, so we have the x cannot be negative 2. And we have, for the domain, okay, we have those values of x less than negative 2, and those values of x greater than negative 2. Again, r of x is already in simplest form, so that means x plus 2 does not cancel out. So the restricted value here is going to be the vertical asymptote. Now, in terms of any other asymptotes, okay, so this comes down to degree comparison. And I'll just mention, okay, see we have like with 3x plus 1 over x plus 2. Now the degrees in the expression nx, okay, will be at 1. Okay, so again we have n is equal to 1. And guess what? In the denominator, highest order term is x, and this is also a first order. And so when we have the n is equal to m, and once again, if the degrees are the same, we're going to have a horizontal asymptote. And this will be taking the ratio of the highest order terms. Okay, so we're going to have a horizontal asymptote. So we have from 3x plus 1 higher order term, we're going to have a 3x. From x plus 2, I have the higher order term at x, so y is equal to 3x over x. And so this is going to be at 3. So we have two asymptotes, one vertical at x equal to negative 2, and the other one we have the horizontal asymptote at y is equal to 3. So we have in the case of the behavior of this graph. Okay, so we have a couple of asymptotes. Again, the vertical asymptote we have at x is equal to negative 2. And the horizontal asymptote, okay, we have y is equal to 3. And just with our function r of x. Now there'll be some rational functions where you could have contact with the horizontal asymptote, but again, vertical asymptotes are going to be off limits. Okay, now for this function r of x, you will have to run tangent to both the vertical and the horizontal asymptotes. So again, both of these sections are in reference to r of x equals 3x plus 1 all over x plus 2. Now let's say we have another rational function, okay, and we'll keep this one basic. Okay, so we'll say we have r of x is equal to 3 over x plus 4. Okay, so we have one denominator expression, so we have one exclusion. So we have x plus 4 cannot be 0. So we have the x cannot be negative 4. And once again, we have with the domain, okay, we have those values x less than what is excluded. And then you'll have those values x that will be greater than what is excluded. So in this case, the excluded value we have at negative 4. And again, we have r of x is already simplified. We're already in simplest terms. So that means that the excluded value negative 4, okay, that is going to define the vertical asymptote. And just looking at what we have in terms of any other type of asymptote. Okay. And what's going to happen here, okay, is that, okay, so you have x plus 4 in the denominator. Okay, so this is going to be a first order. So at least the denominator degree is going to be at 1. Okay, now for the numerator, okay, you do not see an x term present. So for what this is going to mean is that n is equal to 0. So if you have just a constant, then the degree is going to be 0. Okay, so you have no x term. And in terms of how n and m are going to relate, well, 0 is less than 1. So again, we had the first case where if the degree of the numerator is less than what is in the denominator, then there will be a horizontal asymptote, and that is automatically going to be y is equal to 0. So in the case of what we have regarding the features, okay, so you have two asymptotes, one vertical and the other one, once again, horizontal. Okay, so you have a vertical asymptote. Okay, so you have x is equal to negative 4, and for y is equal to 0. Okay, so that is going to be the x-axis. Okay, so you have y is equal to 0 at the x-axis. And since there is no denominator factor canceled, since r of x is already in simplest form, okay, you're going to have no hole in the graph. And just for what we have in the case of r of x, again, this is going to be split up into two regions here. And this will run tangent to both the horizontal asymptote as well as the vertical asymptote. All right, and for what we have, say just to kind of round things out, okay, so we have as a third case here, we have a rational function. Okay, so you have r of x, and we have equal to, in this case, all right, we have x cubed plus 3x squared plus 4x plus 1 and we have all over x squared plus 1. Okay, and let me mention, okay, so for this particular ratio, okay, if I'm trying to find out any exclusions from the domain, now this ratio is already in simplest form. So again, we have x squared plus 1 cannot be 0. And I cannot factor a sum of squares. And guess what? I have x squared cannot be negative 1. And again, if I reapply the square root property of equality, so I have x cannot be plus or minus the square root of negative 1. So you have x cannot be plus or minus I. But guess what? We're not working with complex numbers. So you have no real values excluded. And we're not working with a complex number system. And the only way for x squared plus 1 to not be 0 would be for those numbers to be not real but complex numbers. So there are no real values excluded. And so this means in consequence, okay, that there is no vertical asymptote. And also, since no real values are excluded, the domain will be the set of all real numbers or again, an interval notation, so you have going between negative and positive infinity. And also we have no vertical asymptote. Okay, so there's no vertical asymptote, okay, but there still exists the possibility of there being an asymptote period. Okay, so in the degree comparisons, okay, you have the numerator, okay, is going to be third order in x. And the denominator, okay, we have second degree. And looking at how the numbers are going to line up. Okay. Again, so we have the n is going to be greater than m by 1 degree. So we're going to have a slant asymptote. and in terms of what this slant asymptote is going to be. Okay, so this is going to come from polynomial division. And you have the divisor. Okay, so you have x squared. And you can use, even with divisors, you can use zeros for placeholders. I did not use it before, but you can use it. In this case, you have x squared plus 0, x plus 1, or x squared plus 1. And we have taking into x cubed plus 3x squared plus 4x plus 1. Okay, so we have x squared into x cubed, or x cubed divided by x squared becomes x. And looking at distributing, so you have x over x squared becomes x cubed, x times 0x, you just regard that as 0x. And we have plus x. Now I'll just color code here. Again, you don't have to write the 0x, but you'll just have like a gap that exists here. So we have, with subtracting, x cubed goes out, and we're going to bring down 3x squared. And we have 4x minus x leaves us with 3x, and we can bring down the plus 1. And then x squared into 3x squared will go 3 times. And distributing 3 over x squared, so you have 3x squared. And again, we have plus 0. Once again, essentially, and then we have plus 3. And we have, again, with subtracting, 3x squared goes out, and we got 3x. 1 minus 3 becomes negative 2. And guess what? I cannot take x squared directly into 3x. So I have left standing, okay, I have x plus 3. And this quotient, that is going to define our slant asymptote, or in this case, we had that y is equal to x plus 3. Okay, and we'll be looking at applications, okay, where we have slant asymptotes along with horizontal asymptotes.